Hello everyone. Here we'll be discussing 2.4, which is the precise definition of a limit. Now I'll be quite honest, I'm not going to be emphasizing on things too much because I don't really feel that this section is of great importance as far as practicality goes, but it is of great importance as far as understanding goes. In other words, you won't be tested on any of this material directly, at least in my eyes. Other people may have different priorities as far as feeling this is more important than I feel it is, but I feel that actually using techniques to find limits opposed to understanding a precise definition of what it means to be close to something, you know, I feel that the techniques are more important. But anyways, let's kind of get on with it here. So here I say recall that our notation, limit as x approaches a of f of x is equal to L, basically means that f of x approaches L as x approaches a. And this arrow, of course, means approaches, and it means it gets close to. Now, what exactly it means to be close to something, we're going to hone in on that idea there, because that idea is kind of mathematically vague. We're going to try to describe that a little more with mathematics. So the precise definition here basically says, if for every epsilon bigger than 0, there is a delta bigger than 0, such that such that this statement is true. So let me start with this statement here. And it says, if 0 is less than the absolute value of x minus a less than delta, then the absolute value of f of x minus L is less than epsilon. Now, what does this mean? Well, it basically says that when x is really close to a, the difference, the absolute value of the difference between x and a will be small, so it's going to be less than some number, some really, really, really small number. Then f of x is close to L, meaning that the difference between f of x and L in absolute value is less than another small number. Now specifically it says we can actually pick any number epsilon, so we can actually choose these to be as close as we want, and we can always find a number such that x and a are close accordingly. So I know it still sounds weird, but let me try to explain with a graph a little bit. So let's just imagine here we have a visualization, our xy plane, and let's just say that this is f of x, and let's say we're trying to find the limit as x goes to a of f of x, and that's L. So again, we're basically trying to plug it in. We're trying to plug a into f, but for whatever reason, let's say we can't, so we want to see what happens as x gets closer to a. What does f get closer to? And we're assuming that it gets closer to L, basically, that this limit exists. So what we can kind of do is we can say that if we pick numbers around a and project them to f, so to speak, maybe this image isn't the best, but I guess we kind of see it here. Let's just say something like this. In fact, here it doesn't actually, well, that's fine. It doesn't have to be exactly on the graph itself. It can be the lowest point, let's say, which I know sounds weird, but basically there exists a closeness of L given a closeness on A. So depending how close you want to be to A, we can find a certain closeness about L where we kind of hone in on the limit. Now this distance that we go about as far as being surrounded by A is called delta. So this is kind of like the radius about A, which I know again sounds a little funny, but remember we're picking a number x. So we're picking a number x that's close to A. So how this comes about really is the fact that absolute value basically just means the distance between. So if you have x minus a and you take the difference, you may get a positive or negative number depending on which one's bigger, but if you take the absolute value, you just get a positive number only, and that represents the distance straight up. So if you pick a number x, let's say here or here, this distance will be x minus a, this distance will be negative a, well, it'd be a minus x actually, but what we're trying to say is that this distance is at most delta. So if your x you're choosing is either on the left or on the right, the distance between x and a is equal to delta. So that's what we're calling delta, that distance itself. So this is a way of describing that. At least that's the biggest that distance can be. So that means that if that's the case, then the distance between L and F of x, so notice f of x is actually supposed to be somewhere over here, and this f of x value is actually way over here. But regardless, this distance value here is called epsilon. So probably not the best explanation out there, but again, it's just basically a way to define closeness as far as distances go. And a way to describe distance in mathematics is pretty simple. The distance between two numbers on a number line is just the absolute value of their difference. Good. So we're trying to say the distance is less than an arbitrary real number, so delta and epsilon are usually going to be pretty small. We can find one given the other. Now specifically we want to find delta for every epsilon you can choose. Because if you want epsilon to be really small, that means you want f of x and L to be really close. There exists a delta such that x and a are that close basically. So finally, let's move on to an example where we can actually get our hands dirty with this. Now, this is a little specific, but then afterwards I'm going to do some kind of more hardcore examples. So here I say the limit as x goes to 1 of 3x minus 4. Well, we want to find what the limit is, but with these problems in 2.4, we're not really using this to find the limit. We're just using this to have the understanding of what limits do. So we can just look at this and think DSP, plug in 1, we get 3 minus 4, that's negative 1. So we have an understanding that this is equal to negative 1. So I'll write that in a moment. But specifically, they want us to find delta when epsilon is equal to 0.05. So we kind of already have the understanding. Let me kind of scoot this over. We already kind of have the understanding that this is equal to negative 1. Okay, good. So now we know what epsilon is, and where does epsilon come into play in the definition? It's the absolute value of f of x, which is 3x minus 4, minus L. We know L is negative 1 in this case. That's our L. So this is minus negative 1, and absolute value is less than epsilon, which in our case is 0.05. Now again, we have epsilon, and we want to find delta. Now, where does delta come into play? Delta comes into play when we have this. So how can we find this? Now notice absolute values are always positive. So this part is kind of given, but the reason why we need this is because if it was equality, so notice this is saying it's bigger than 0. So if it was equal to 0, then x would be straight up equal to a, and we're not sure if we can plug in a all the time. So for that reason, that's why that's there. So just kind of throwing that out there. So now notice here this is plus, so we end up getting 3x minus 4 plus 1, which is of course 3x minus 3, in absolute value, is less than 0.05. And notice, these both have 3 in common, so we can actually pull that out even outside of the absolute value, and we get x minus 1 left on the inside. And this is perfect because if you look at where delta comes into play as far as the definition goes, it's the absolute value of x minus a less than a number. Now, our a in this case is what we're approaching, and that's 1. So we want the absolute value of x minus 1 to be less than a number, and we basically have it. All we have to do now is divide by 3, and then we'll get that the absolute value of x minus 1 is less than 0.05 over 3, so that our delta is equal to 0.05 over 3. And I'm just going to leave it like that. And if you want to approximate it, I guess you can. And in fact, since 5 over 3 is 1.666, this is going to be 0.0166. So if you want to find a number that's even bigger than this, you certainly can. But the kind of goal is to make delta small as possible. So this is one example of delta that works, but there are other values of delta that will work as well. So, but this one I think is good. So how you know it works is by plugging it in. So if the absolute value of x minus a is less than 0.05 over 3, then multiplying both sides by 3, kind of running the argument backwards, gives you this, which in turn will give you that after distribution, which in turn will give you this, which suggests that the absolute value of f of x and negative 1, the difference between those, that is, in other words, the distance between them, is less than 0.05. So we found kind of a way to track the distance between x and 1, and that tells us that the difference between our f of x value and our supposed L value are as small as we want it to be. So this 0.05 is an arbitrary number. If they gave us 0.00001, we can find a delta such that that's true. So we can make it so that it's as close as we need it to be. And again, this is a way of describing close from a mathematical sense. Perfect. So now I'm kind of taking a little long here, so now I'm going to transition into those more difficult problems that I was talking about earlier, or we're not actually going to be using these numbers. I'm actually just going to be using epsilon and delta as is, just those Greek letters themselves, and then we'll move on from there. All right, so here we're asked to prove, using that precise definition we just saw, that the limit as x goes to 2 of x squared minus 3x is equal to negative 2. And we can definitely tell by DSP that this is true. Plug in 2, you get 4. 2 squared is 4. Minus 3 times 2 is 6, and 4 minus 6 is indeed negative 2. So intuitively it makes sense, but now precisely how can we prove this? Well, remember that we want to say for all, so this is my proof, let me write PF for proof. So let me say for all epsilon bigger than 0, we want f of x minus L, so this is our f of x, minus our negative 2 to be less than epsilon. So we want that to be the case, and now we want to find delta. So how can we find delta? So we have to kind of work backwards, and then we're going to show that it's true at the very end. So notice that if we try to manipulate this a little bit, we get x squared minus 3x plus 2 in absolute value is less than epsilon. Now, the great news here is that we can actually factor this, believe it or not. This factors as x minus 1 times x minus 2. Now, you probably expect me to write them in parentheses, but I'm going to actually write them each in absolute values. And the reason why we're allowed to do this is because absolute value of a product is a product of the absolute value, so it's just a property, basically. Now, there's one more property I kind of have to show here, have to convince you that we can use it. Now, notice that we want to find delta such that the absolute value of x minus 1 is less than delta. The problem, of course, is we have this big isor of x minus 2, not x minus 1. So can we make this x minus 1 somehow? And we actually kind of can. To do so, we need what is called the triangle inequality. And the triangle inequality says that the absolute value of a plus b is less than or equal to the absolute value of a plus the absolute value of b. And it's kind of hard to describe based on the name, but let me just say the following. If you have a triangle whose side lengths are a, b, and again, it sounds a little weird, but let's just say the absolute value of a plus b, well, notice that if you were to actually add this one to this one, so absolute value of a to the absolute value of b, it's going to be larger than the other side of the triangle. And that's always the case, that actually if you consider any triangle, the sum of the two smaller parts is always going to be larger than this other one. If it was equal to this, then that means it would collapse into one straight line and it wouldn't even be a triangle. Now, the hard part to convince you is that when would you ever have a scenario where this length is the absolute value of a plus b? So to be quite honest, the context of this kind of comes out from basically vectors. So if you treat a and b as vectors, then the absolute value are basically the magnitudes of the vectors. And that's where the name kind of comes from and where this context makes more sense. But if you kind of plug in numbers, you'll see that this is certainly true. Now, if a and b are all positive numbers, then there's no difference here. It's actually equality. And you can kind of test it out with a few different numbers. But when a and b start to be negative, this will start to make more sense as far as what we have less than or equal to. So now that we have an understanding that this is true, hopefully that was okay, I'm going to try to use it with x minus 2. But I want to get x minus 1 involved. So I'm going to write the absolute value of x minus 2 as x minus 1 minus 1. So this is just the absolute value of x minus 2, notice. But by triangle inequality, this is, if we treat this as a, and this negative 1 as our b, and this is less than or equal to the absolute value of x minus 1 plus the absolute value of negative 1. which we can certainly do actually. So notice we get this. Perfect. So we actually get that the absolute value of x minus 2 is less than the absolute value of x minus 1 plus 1 now. Perfect. So now I'm going to erase this and kind of keep working with this part here. So let me just do that right now. So remember, it's less than epsilon. It's for every epsilon. So that's given to us. I think we'll be okay, but let's just kind of think for a moment here. So we have the absolute value of x minus 1 times absolute value of x minus 2, but we know that's actually less than or equal to this. Now, if we're asserting that this is in between that and epsilon, and this is still less than epsilon, and if we distribute this, then we'll get the absolute value of x minus 1 squared plus the absolute value of x minus 1. But recall we want x minus 1 and absolute value to be less than delta. So this should be less than or equal to, in fact it should be less than, because the absolute value of x minus 1 is strictly less than delta. So it'd be less than delta squared plus delta, less than epsilon. Perfect. So we want epsilon to be larger than all of these other parts of the inequalities, which I know sounds kind of weird. So epsilon is given, but we're going to find a delta that's, I guess, kind of not smaller, but we're going to find a delta such that each of these parts is definitely smaller than that epsilon. And we can certainly do that. In fact, here notice that if we call this equality, so if we say this is equal to epsilon, which I know again sounds a little funny, it's kind of like we're making our own rules and breaking things a little bit, but we know that x minus 1 in absolute value is less than delta, and we're going to make it so that that expression here amounts to epsilon. So these are each less than delta, so we get this expression, and we want that to amount to epsilon. So we're getting this. So if I wanted to kind of change things in this to make more sense of things, I'm going to say the following. Like this. So this in absolute value is equal to all of this. This is less than that by triangle inequality, and equal to this by distribution actually. So that's equality here. And then this is less than because of the fact that we want x minus 1 absolute value to be less than delta, and we want this to amount to epsilon so that this whole original inequality is less than epsilon. So I think that makes a little more sense, hopefully. But now notice that this equation we can actually solve for delta in terms of epsilon using the quadratic formula. So let's see if we can do that. We have delta squared plus delta minus epsilon is equal to 0. So in this case, using quadratic formula, a is 1, b is 1, and c is negative epsilon. So that we have delta is equal to, by the quadratic formula, negative b plus or minus the square root of b squared minus 4 times a times c. Since c is negative epsilon, this becomes a positive here, which means we don't have any issues with a negative inside of the radical, all divided by 2 times a. Now the only real issue is we have this plus or minus to deal with. I guess we can choose the positive one. Does it really matter? I don't think it really matters, but we can choose the positive one if we like. So I'm just going to choose the positive one because it'll give us a larger number. If we choose negative, then it'll be a negative value actually. And since we want delta to be positive because it's going to be bigger than a positive number, it doesn't make sense actually to choose negative. So let's choose the positive one here. That I think makes more sense. So delta is going to be equal to negative 1 plus the absolute value of 1 plus 4 epsilon all over 2. Perfect. So we have found delta such that for any epsilon we choose, we can find delta in terms of epsilon. Great. So for all epsilon bigger than 0, there exists a delta such that the precise definition will happen. Now that part I actually haven't shown yet. So I'm going to erase this and actually show that so we can prove that the limit of this expression is indeed equal to negative 2. Right, so now we're able to say that for all epsilon bigger than 0, we can choose delta equal to this expression in terms of epsilon. Now again, the precise definition said for all, so it's kind of a universal quantity of epsilon, there exists, so that's like an existence of delta. So we can select any delta based on the epsilon that we're given. So for any epsilon, we can choose this delta in terms of epsilon. And if, so now that big statement and the precise definition, the if-then part comes into play. So if the absolute value of x minus 1 is less than delta, which is equal to this expression here, then, well, we want to show that, well, the absolute value of the difference between this and -2 is less than epsilon. And we can do that basically by running what we just discovered in reverse. So to do that, I'm going to first find out what the absolute value of x minus 1 squared is less than, and that's of course less than delta squared. Now delta squared is going to be this fraction squared, so the top squared over the bottom squared, so the bottom is going to be 4 for sure. Now when you square this binomial, -1 plus that radical, remember how we've expanded those before, that's going to be the first one squared, which is +1, plus 2 times their product, which is going to be 2 times that radical part, plus the last one squared, which will break the radical. Great. Now if you actually manipulate this a little bit, what this ends up combining to is 2 plus 4 epsilon minus 2 times that radical, all over 4. Now since the top and bottom are both even, we can divide by 2, and basically that'll become a 1, and this will become a 2, that'll become a 1 times that radical, and then dividing the 4 by 2 gives that 2. So it actually combines into this. And notice that if we actually add x minus 1 absolute value squared to the absolute value of x minus 1, that's going to be certainly less than delta squared plus delta, because each of these are less than delta squared and delta respectively. So we're going to add this to the original delta. So notice doing that will cancel the radicals and actually cancel the -1s. So that'll just give you, well, let's see. If you actually add those, you'll get 1 plus 2 epsilon minus that radical expression, 1 plus 4 epsilon in the square root. That's the square, plus delta, which is all over 2 as well. So we can just write plus, or I guess minus 1 plus, that radical expression. And then that's all over the same common denominator 2. But now notice here what happens is that the 1's cancel as well as the radicals. So all we're left with really is 2 epsilon over 2, where the 2's actually cancel, and that's just equal to epsilon. Perfect. But again, we're not quite done, because what does this exactly mean in terms of the original function? Well, I'm going to collapse this and then show that finally. Okay, so I've really just erased the work here and written our kind of consequence or result, that the square of the absolute value of x minus 1 added to the absolute value of x minus 1 is less than delta squared plus delta, which is actually equal to epsilon with a little bit of algebraic manipulation. And we want to show that if the absolute value of x minus 1 is less than delta, then we want to say that the absolute value of f of x minus -2, which is plus 2 in absolute value, is somehow less than this. And we know, of course, that this is equal to x minus 1 in absolute value times x minus 2 in absolute value, and we know by the triangle inequality that this is less than or equal to x minus 1 times the quantity x minus 1 plus 1, like this. And that's because x minus 2 in absolute value is, well, it's equal to x minus 1 minus 1 in absolute value, which is less than or equal to, by triangle inequality, absolute value of x minus 1 plus absolute value of -1, which is just 1 itself. And then after distribution, this is actually equal to this expression, which is less than epsilon. So now collapsing all of this, we can say with certainty that, well, the absolute value of our f of x minus our supposed limit -2 is less than epsilon. Perfect. And what does that tell us? So let me erase the work here to kind of So the if then, the then part is really all this and everything else that we shown before that. So now we can say with certainty that this is true. So by the precise definition of limit, we can say with certainty that the limit as x goes to 1 of this expression x squared minus 3x is equal to that limit negative 2. And that completes the proof, and we can write a tombstone here for the completion of proof. Now, something I want to say before we move on, because we're going to talk about just a little bit more, but I'm going to be a little more quick about things hopefully, is that this area of mathematics is known as analysis, mathematical analysis. In fact, it's specifically known as what is called a real analysis, where you talk about the analysis of real numbers, basically. It's kind of like just calculus, but more definition heavy. It's using this. Now, if you ever get into a real analysis course or beyond, my hat's off to you. It's not the easiest stuff in the world, and you have to know definitions like this, and you'll actually be finding limits and proceeding with calculus like this. We won't, though. In a traditional calculus class, this is just shown so we have the understanding that it is a thing, but we won't actually be ever dealing with this ever again once we get to past 2.4. So I'm just kind of making that clear if I haven't made it clear already. So now, before we finish 2.4, the last thing I want to talk about in 2.4 is going to be infinite limits. And we saw that in 2.3. We saw the intuitive understanding of what it means for something to approach infinity or even negative infinity as x approaches a certain number. And basically it was a vertical asymptote is the intuitive graphical understanding of that as far as that goes. But now we're going to see it in a precise manner, and I'm just going to show you one example. It's going to be rather quick, but at least we'll see that it's certainly a thing. So let's take a look at that example right now. All right, so here I want to recall, kind of like how we recalled at the very beginning, definition of limit. If the limit as x goes to a of f of x equals infinity, this means as x gets closer to a, f of x approaches infinity, meaning it gets larger and larger and kind of out of control, just bigger and bigger. So the precise definition here is that for every positive number, capital M, there is a delta bigger than 0 such that this statement holds. If the absolute value of x minus a is less than delta, then f of x is larger than m. So any number you pick, any large number you pick, we can always find a delta such that x, the difference between x and a is less than that delta, will actually imply that our f of x value is larger than the number you chose. So if you choose m to be 1 million, we can find a delta such that x and a are close, so the absolute value is less than that number delta, so it's going to be in terms of m basically, such that f of x is bigger than 1 million. Okay, so now I'm going to do again just one example here. I'm going to prove that the limit as x goes to 0 of 1 over x squared is equal to infinity using this definition. So we want to say for every, so let me just write proof here for starters. So for every epsilon bigger than 0, we want the absolute value of, well, we don't want the absolute value of anything to be less than anything else like normal, but instead we want f of x to be bigger than m. So we want, WTS stands for want to show. We want to show that 1 over x squared is bigger than m. So let's see, how can we use this and work backwards to get that the absolute value of x minus 0 in our case is less than some number delta in terms of m possible? Well, notice x squared is in the denominator here, so I'm going to reciprocate both sides. So if you reciprocate both sides of this inequality, you get that x squared is bigger than m. And this certainly works when everything's positive. If you have two positive numbers in a specific inequality, you can always reciprocate both sides and flip the inequality as a consequence. So that's certainly true. And now we can square root both sides because, again, everything inside is positive. And notice this makes sense because even if we're approaching x equals 0 from the left or from the right, x squared is positive regardless. So now this implies that the square root of x squared is less than the square root of m. Perfect. In fact, you know what? I didn't reciprocate this, did I? So the reciprocal of 1 over x squared is x squared. The reciprocal of m is 1 over m. My mistake. So now if we square root 1 over m, that's 1 over radical m, like that. Perfect. And we're actually done, because as it turns out, the square root of x squared is actually equal to the absolute value of x. Now you may think it's just x itself, but not really, because when x is negative, like imagine x is negative 2, negative 2 squared is 4, and the square root of 4 is just positive 2, not negative 2. And it's because when you square a number, you get a positive number anyways, regardless. So it's not just the original x value you had, it's the absolute value of x, kind of technically. So perfect. So now we can say for every epsilon bigger than 0, we can choose delta to be 1 over radical m. So let's just write that here. Choose delta to equal 1 over the square root of m. Perfect. And now we can say if the absolute value of x minus 0, which is just the absolute value of x, is less than this delta, then this actually implies that 1 over x squared is bigger than m. And again, to actually show that, you'll basically run through the same argument I did, but in reverse. Because since this delta is equal to 1 over radical m, we can reciprocate both sides to get 1 over, let me just kind of show you, 1 over the absolute value of x is bigger than the reciprocal of delta, which is just radical m. And then if you square both sides, you'll get exactly this actually, that 1 over x squared, because absolute value of x squared is just x squared because it's always positive anyways, and then m squared is just m. Radical m squared is just m. Perfect. So this shows by our precise definition that the limit holds. So the limit as x goes to 0 of 1 over x squared is indeed equal to infinity by our precise definition. And that finishes the problem and also the video. Now, there are some things in 2.4 that I didn't talk about. I think that this is enough, of course. It's kind of a lot, but this is enough to get that idea. Some things I didn't talk about, just to kind of throw them out there and give some honorable mentions, so to speak, are one-sided limits. So there are precise definitions for one-sided limits, but it's basically the same thing that we saw as far as the precise definition goes. The definition is just tweaked a little bit so that we're only plugging in numbers that are bigger than or less than whatever we're approaching. All right, so again, 2.4, it's not everyone's cup of tea, but I hope you enjoyed it for what it was, and I'll see you in the next video for 2.5 and beyond that. Hope you enjoyed. Thanks for watching, and I'll see you then.